Welcome to the 36th day of Just Start Programming, the Rust programming language. Today we will start looking into the advanced feature of Rust, mainly the unsafe Rust and advanced traits. So let's see how much we can cover today. And as usual, join me once again live in one take, no shortcuts and no secrets. So let's just start programming. All right, so yesterday I think uh, I was rushing through this topic, so let's go through once again pattern syntax, patterns, and matching in Rust. Let's start from here and see what we missed. All right, so for pattern syntax, the underscore would represent others. So if it doesn't match 1, 2, and 3, aside from 1, 2, and 3, underscore represents anything else. So it can be applied on some, and none. Yeah, so here, X, if it's not some, then else or others would print this default case, or it could be the default behavior. What else do we have here? Okay, so the pipe syntax would represent the OR operator. So we can do 1 or 2 and then execute the statement. Anything else with the underscore would print anything. And then we also have matching ranges of values. I think in the first few days we might have seen this, and first time I'm seeing this, it looks a bit strange, but here we are. Dot dot equal syntax allows us to match an inclusive range of values. So meaning one, let me just move my mic. 1, 2, 5 with 5 inclusive. You can also do something like this. It looks like a chain of OR statements, 1 or 2 or 3 or 4 or 5. You can even do something like this, a character from A all the way to J. Okay, so this is assuming it's an ASCII letter. Yeah, so that equals would mean including J or equals including Z. Anything else, underscore, is something else. Okay, it can be used for destructuring, also for structs. So for example, if you have point, struct point, X and Y, you can do it like this. So P can be assigned to a new point also, where A here will have the value of 0 and 7 will have, B will have the value of 7. Yeah, or it can be done like this as well. And then in match, it's also possible to have the struct itself. On the x-axis at x. Okay, so x, I think, let's see. X could be anything, it seems, whereas y could be 0. On the y-axis y. So y could be anything also, as long as x is at 0. So x and y neither on x and y. Enums, destructuring enums just like structure can be done like this as well, where you have message, quit, move, write, change color. So message, in this case you have double colon, quit. Here move will take on x and y values. So any x and y, as long as it's an enum move. Okay, so here also write, and then you have a string. So any string represented by text, as long as it's an enum message write, so it will be displayed here. Okay, so similar to change color. Okay, same for color, where you have this. Oh, so for color, it could either be RGB or HSV. Yeah, but when we do match, it has to be used here. Then anything else, this parenthesis would mean it's like, yeah, do nothing. Structs and tuples. So there's this possibility as well. You can do something like this. For example, you have struct inside a tuple, and a tuple, I think this is a tuple inside a tuple. It's possible as well. Okay, ignoring values in a pattern. An entire value with underscore. Okay, so underscore. So it's a wildcard pattern. Will match any value but not bind to the value. Okay, so y I32x. What happens to x here in this case? Using underscore in a function signature. Okay, so any value 3. Even if you put in 3, the print line will only consider y. Parts of a value with a nested okay, wait, I think there's an important point here. In most cases, when you no longer need a particular function parameter, okay, yeah, so here this code will completely ignore the value 3, mainly because there's an underscore here. Passes the first argument and will print this one. In most cases, when you no longer need a particular function parameter, you could change the signature so it doesn't include the unused parameter. Ignoring a function parameter can be especially useful in cases, for example, you're implementing a trait when you need certain type signature, but the function body in your implementation doesn't need one of the parameters. So for traits, it's like a contract and how your function will look like. So it was saying here that, for example, one parameter is actually not really needed. So you can ignore by putting in underscore. Parts of a value with a nested underscore. Okay. Parts of a value with nested. Okay, we can see here you have some underscore, then you have underscore here. This code will print can't override an existing customized value, and then setting is sum 5. Okay, so this one will print in the first match arm. We don't need to match on or use the values inside either sum variant, but we do need to test for the case when setting value and new setting value are the sum variant. In that case, we print the reason for not changing setting value. It doesn't get changed. Okay, so this is just to check or to test when setting value and new setting value are the sum variant. Yeah. So these two things here. If it matches sum 2 of the sum variant, then print. Can also use underscore in multiple places with one pattern to ignore particular values. Okay, so 4 will be ignored, 16, yeah, 4 and 16 will be ignored. Unused variable by starting its name with underscore. Okay, so x, I think in some compilation error, we might have seen this, where it's suggesting if it's unused, you put underscore like this. Here we get a warning about not using the variable y, but we don't get a warning about not using underscore x. So maybe if it's a placeholder, then you can put underscore. Okay, remaining parts with value dot dot. Okay, so I think just like in range, the dot dot pattern ignores any parts of value that we haven't explicitly matched in the rest of the pattern. So x, we have x here as part of the struct, so y and z can be ignored with the dot dot. Or another way of doing it is you have underscore, comma, underscore. Yeah, like this. The syntax dot dot will expand to as many values as it needs to be. So you don't need to, for example, if you have a long list, then you don't need to put underscore, underscore, underscore all throughout. You can just put dot dot. Oh, I think this one is special. Mainly first, then last. Oh, this one will not compile. Can only be used once per tuple pattern. As either, yeah, so this could be some variable name, and then you have a dot dot, so that you'll only be using this once in a tuple. Extra conditionals with match guard. So match guard. What is a match guard? So there's an expression within match. So you can have something like this also. And it needs to evaluate to true or false, perhaps. Yep. Mhm. So you can have or, and then you have if y should be true or false. Bindings, I think we have skipped this part yesterday, so let's read through what exactly is the at sign. So the at operator lets us create a variable that holds a value. At the same time, we're testing that value for a pattern match. Hold the value and test for pattern match. Okay, here we have message hello ID field within the range 3 to 7. Once you see equal, then it's inclusive of 7. You also want to bind the value to the variable ID variable so we can use it in the code associated with the ARM. We could name this variable ID the same as the field, but for this example we use a different name. Okay, so let's see. ID variable at sign 3 to 7. I could name this variable ID. Okay, ID. So it's inside. Okay, this is an enum. This is the scope of the enum. And then you have a block for ID variable. Where's the ID variable? ID variable at 3 to 7. And then ID will hold the value. In this example, we print found an ID in range 5. Found an ID in range 5. Okay, so message hello is actually this. ID is 5. So 5 at, so this part is evaluated at 3 to 7. 3 to 7. Okay. We're capturing whatever the value match the range while also testing that the value match the range pattern. The second arm, we only have a range specified in the pattern. Okay, so this one doesn't capture anything but just a range. So the ID field's value could have been 10, 11, or 12. The code that goes with that pattern doesn't know which it is. Okay, so it doesn't know which one. The pattern code isn't able to use the value from the ID field because we haven't saved the ID value in a variable. So this one will not be printed. Okay, in the last arm, we've specified a variable without a range. So it's just variable. We do have the value available to use the arms code in variable named ID. The reason is that we've used the struct field shorthand syntax, but we haven't applied any test to the value in the ID field, this arm, as we did with the first two arms. Any value would match this pattern by specifying the ID. Yeah, any value will match pattern. So it means finally found some other ID. This one. Or does it go in sequence? I think it will go in sequence. Using at sign lets us test the value and save it in a variable with one pattern. Yeah, so this one will be satisfied. Okay, so we are done with that. I think now we can move on to the advanced features in Rust. Okay, so almost there, almost at the finish line. Advanced features. By now you've learned the most commonly used parts of the Rust programming language. Before we do one more project in chapter 21, which is to build a multi-threaded web server, we'll look at a few aspects of the language you might run into every once in a while, but many not use every day. But may not use every day. You can use this chapter as a reference for when you encounter any unknowns. The features covered here are useful in very specific situations. Although you might not reach for them often, we want to make sure you have a grasp of all the features Rust has to offer. In this chapter, we'll cover unsafe Rust, how to opt out of some Rust guarantees and take responsibility for manually upholding those guarantees. Advanced traits, associated types, default type parameters, fully qualified syntax, super traits. Oh, so there are super traits. And a new type pattern in relation to traits. Advanced types. More about the new type pattern, type aliases, the never type, and dynamically sized types. Advanced function enclosures, function pointers and returning closures. Macros, ways to define code that defines more code at compile time. I think we came across a lot of macros already. Vector macro, debug macro. Yeah, so it would be interesting to know and come up with our own macros as well. Panoply of Rust features with something for everyone. Let's dive in. Okay. So let's start with unsafe Rust. All the code we have discussed so far has Rust memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside it that doesn't enforce these memory safety guarantees. It's called Unsafe Rust and works just like regular Rust but gives us extra superpowers. Unsafe Rust exists because, by nature, static analysis is conservative. When the compiler tries to determine whether or not code upholds the guarantees, it's better for it to reject some valid programs than to accept some invalid programs. Although the code might be okay, if the Rust compiler doesn't have enough information to be confident, it will reject the code. Yeah, so I think this part was mentioned previously also, where the compiler couldn't tell, or it's not confident at all. So it will take the conservative approach and ensuring you're doing safe code. So it will reject, then the compiler will throw an error. In these cases, you can use unsafe code to tell the compiler, trust me, I know what I'm doing. Be warned, however, that you use unsafe Rust at your own risk. If you use unsafe code incorrectly, problems can occur due to memory unsafety, such as null pointer dereferencing. Another reason Rust has an unsafe alter ego is that the underlying computer hardware is inherently unsafe. If Rust didn't let you do unsafe operations, you couldn't do certain tasks. Rust needs to allow you to do low-level system programming, such as directly interacting with the operating system or even writing your own operating system. Working with low-level system programming is one of the goals of the language. Let's explore what you can do with unsafe Rust and how to do it. Unsafe superpowers. To switch to unsafe Rust, we use use the unsafe keyword. Okay, so there's another new keyword here, unsafe. And then start a new block that holds the unsafe code. You can take 5 actions in unsafe Rust that you can in safe Rust, which we call unsafe superpowers. So it says there are 5. Those superpowers include the ability to dereference a raw pointer, call an unsafe function or method, access or modify a mutable static variable. Mutable. Okay, mutable variable. I think we might have done this before, where we're updating immutable. No, okay, I think that's the other way around. Changing immutable variable. Yeah, I think we have done that last time. Implement an unsafe trait. Implement an unsafe trait. Access fields of a union. Okay, union is something new. It's important to understand that unsafe doesn't turn off the borrow checker or disable any Rust other safety checks. If you use a reference in unsafe code, it will still be checked. The unsafe keyword only gives you access to these 5 features that are then not checked by the compiler for memory safety. You'll still get some degree of safety inside of an unsafe block. In addition, unsafe doesn't mean the code inside the block is necessarily dangerous, but that it will definitely have memory safety problems. The intent is that as the programmer, you ensure the code inside an unsafe block will access memory in a valid way. People are fallible, and mistakes will happen. But by requiring those 5 unsafe operations to be inside blocks annotated with unsafe, you know that any errors related to memory safety must be within the unsafe block. Keep unsafe blocks small. You'll be thankful later when you investigate memory bugs. So unsafe block is like a marker. Marker for you to check later on that memory safety could be due to some unsafe block. To isolate unsafe code as much as possible, it's best to enclose such code within a safe abstraction and provide a safe API, which we'll discuss later in the chapter when we examine unsafe functions and methods. Parts of the standard library are implemented as safe abstractions over unsafe code that has been audited. Wrapping unsafe code in a safe abstraction prevents uses of unsafe from leaking out into all the places that you or your users might want to use the functionality implemented with unsafe code, because using a safe abstraction is safe. Okay, so it says here wrapping unsafe code in a safe abstraction prevents uses of unsafe from leaking. Okay. Let's look at each of the 5 unsafe superpowers in turn. We'll look at some abstractions that provide a safe interface to unsafe code. Dereferencing a raw pointer. Okay, so in dangling references in chapter 4, we mentioned that the compiler ensures references are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to references. As with references, raw pointers can be immutable or mutable and are written as star const and star mot. So there's a star. Yeah, because we are dereferencing const or mot. The asterisk isn't dereference operator. Oh, it's wrong. It's part of the type name. In the context of raw pointers, immutable means that the pointer can't be directly assigned. Can't be directly assigned to after being dereferenced. Okay, so the concept of immutability is applied here, mainly in the aspect of it can't be directly assigned to after being dereferenced. Once it's already dereferenced, then it cannot be assigned to. Different from references and smart pointers, raw pointers are allowed to ignore the borrowing rules. By having both immutable and mutable pointers or multiple mutable pointers to the same location. Oh, this is interesting. Having both immutable and mutable pointers or multiple mutable pointers to the same location aren't guaranteed to point to a valid memory, are allowed to be null. Don't implement any automatic cleanup. Yeah, so this is how raw it can get. By opting out of having Rust enforce these guarantees, you can give up guaranteed safety in exchange for greater performance. How can we achieve greater performance? Or the ability to interface with another language or hardware where Rust guarantees don't apply. Okay, so this one shows how to create an immutable and mutable raw pointer. Okay, here we have a mutable variable. R1 equals to reference. Oh, okay, so we have a reference raw constant. No, so I think constant makes it immutable. MUT makes it mutable. So ampersand raw, either const or mut. Notice that we don't include the unsafe keyword in this code. We can create raw pointers in safe code. We just can't dereference raw pointers outside of an unsafe block. You'll see in a bit. Okay, so we have created a raw pointers by using raw borrow operators at raw ampersand raw. Const num creates a star const I32 immutable raw pointer, and ampersand raw mut num creates a star mut I32 mutable raw pointer. Because we create them directly from a local variable, we know these particular raw pointers are valid, but we can't make that assumption about just any raw pointer. To demonstrate this, next we'll create a raw pointer whose validity we can't be so certain of, using as to cast a value instead of using the raw borrow operator. Listing 20-2 shows how to create a raw pointer to an arbitrary location in memory. Arbitrary location in memory. Trying to use arbitrary memory is undefined. There might be data that address or there might not. Compiler might optimize a code so there's no memory access. Or the program might terminate with a segmentation fault. Usually there is no good reason to write code like this, especially in cases where you can use a raw borrow operator instead, but it's possible. Okay, so creating a raw pointer to an arbitrary memory address. Recall that we can create raw pointers in safe code, but we can't dereference raw pointers and read the data being pointed to. So in listing 20-3, we use the dereference operator on a raw pointer that requires an unsafe block. Okay, so for R1, you want to dereference R1, so it has to be inside this unsafe block. Creating a pointer does no harm. It's only when we try to access the value that it points at that we might end up dealing with an invalid value. Note also that in listing 20-1 and 20-3, we created asterisk cons I32 and mot I32 raw pointers that both pointed to the same memory location where nav is stored. The code would not have compiled because Rust ownership rules not allow mutable reference at the same time as immutable references. With raw pointers, we can create a mutable pointer and an immutable pointer to the same location and change data through the mutable pointer. We can change the data through a mutable pointer, potentially creating a data race. Careful. With all of these dangers, why would you ever use raw pointers? One major use case is when okay, so this is nice. One major use case is when interfacing with C code, as you'll see in the next section, calling an unsafe function or method. Another case is when building up safe abstraction that the borrow checker doesn't understand. You introduce unsafe functions and then look at an example of safe abstraction that uses unsafe code. Okay. Calling an unsafe function or method. The second type of operation you can perform in unsafe block is calling unsafe functions. Unsafe functions and methods look exactly like regular functions and methods, but they have an extra unsafe before the rest of the definition. The unsafe keyword in this context indicates the function has requirements we need to uphold when we call this function. Because Rust can't guarantee we've met these requirements, okay, by calling an unsafe function within an unsafe block, we're saying that we've read this function's documentation and we take responsibility for upholding the function's contracts. Here's an unsafe function named dangerous that doesn't do anything in its body. Unsafe fn. Unsafe and dangerous. We must call the dangerous function within a separate unsafe block. If we try to call dangerous without a safe block, we'll get an error. So the compiler will scream call to unsafe function. With the unsafe block, we're asserting to Rust that we have read the function's documentation, we understood how to use it properly, and we have verified that we are fulfilling the contract of the function. To perform unsafe operations in the body of an unsafe function, you still need to use an unsafe block, just as within a regular function. And the compiler will warn you if you forget. This helps to keep unsafe blocks as small as possible, as unsafe operations may not be needed across the whole function body. Creating a safe abstraction over unsafe code. Just because a function contains unsafe code doesn't mean we need to mark the entire function as unsafe. In fact, wrapping unsafe code in a safe function is common abstraction. As an example, let's study the split at mod function from the standard library, which requires some unsafe code. Okay, so there's already unsafe code like this in the standard library. We'll explore how we might implement it. This safe method is defined on mutable slices. It takes one slice and makes it two by splitting the slice at the index given as an argument. Listing 20-4 shows how to split at mat. Okay, so we have a vector macro containing 1 to 6. Okay, so V reference a mutable V, okay, R. Then you have split at mat. We can't implement this function using only safe Rust. An attempt might look something like listing 20-5, which won't compile. For simplicity, we'll implement split at mat as a function rather than a method, and only for slices of I32 values rather than for a generic type T. Okay, so what's in here? Split at mat. This one will not compile. 1, 2, 3. So 1, 2, 3. Is there another one? An attempted implementation of split at mat using only safe Rust. This function first gets the total length of the slice, and then it asserts that the index given as parameter is within the slice by checking whether it's less than or equal to the length. Okay. The assertion means that if we pass an index that is greater than the length to split a slice at, the function will panic before it attempts to use that index. Then we return two mutable slices in the tuple, one from the start of the original slice to the mid index and another from mid to the end of the slice. When we try to compile the code, we'll get an error. Okay, so here, second mutable borrow occurs here. Okay. Okay, because values, okay, here, second mutable borrow occur here. The first is here. Rust borrow checker can't understand that we are borrowing different parts of the slice. It only knows that we are borrowing from the same slice twice. Borrowing different parts of a slice is fundamentally okay because the two slices aren't overlapping. But Rust isn't smart enough to know this. When we know code is okay, but Rust doesn't, it's time to reach for unsafe code. Listing 20-6 shows how to use an unsafe block, a raw pointer, and some calls to unsafe functions to make the implementation of split at mat work. Okay, so what's happening here? First, you have unsafe block, slice from raw parts. This one has only this. Slice from raw parts mat. PTR. What is PTR? Okay. As mat PTR. Recall from the slice type in chapter 4 that slices are a pointer to some data and the length of the slice. Use the len method to get the length of a slice and the asmatptr method to access the raw pointer of a slice. In this case, because we have a mutable slice to I32 values, as matptr returns a raw pointer with the type star mat I32, which we've stored in the variable ptr. Variable, okay, here. Okay, this part is explaining this part. We keep the assertion that mid index is within the slice. Then we get to the unsafe code. The slice from raw parts MUT function takes a raw pointer, okay, raw pointer and length, and it creates a slice. We used to create a slice that starts from ptr and is mid items long. Then we call the add method on ptr with mid as an argument to get raw pointer that starts at mid. And we create a slice using that pointer and then the remaining number of items after mid as length. Okay. The function slice from raw parts mat is unsafe because it takes a raw pointer and must trust that this pointer is valid. The add method on raw pointers is also unsafe. What is that? Okay. Because it must trust that the offset location is also a valid pointer. Therefore, we had to put an unsafe block around our calls add so we could call them. By looking at the code and by adding assertion that mid must be less than or equal to len, we can tell that all the raw pointers used with unsafe block will be valid pointers to data within the slice. This is an acceptable and appropriate use of unsafe. Okay. Note that we don't need to mark the resultant split at mod function as unsafe. Split at mod, that's it. Okay, this whole function. And we can call this function from safe rust. We've created a safe abstraction to the unsafe code with an implementation of the function that uses unsafe code in a safe way. Because it creates only valid pointers from the data, this function has access to. In contrast, the use of slice from raw parts mat in listing 20-7 would likely crash when the slice is used. This code takes an arbitrary memory location and creates a slice. Okay. We don't own the memory at this arbitrary location, and there is no, okay, this part. There is no guarantee that the slice this code creates contains valid I32 values. Attempting to use values as though it's a valid slice results in undefined behavior. Okay. Using external functions to call external code. Sometimes your Rust code might need to interact with code written in another language. For this, Rust has a keyword extern that facilitates the creation and use of a foreign function interface and an FFI, foreign function interface, is a way of programming language to define functions and enable a different foreign programming language to call those functions. Okay, so this one demonstrates how to set up an integration with ABS. Okay, integration with ABS. Function from the C standard library. ABS as in absolute. Functions declared within the extern blocks are generally unsafe to call from Rust code, so extern blocks must also be marked unsafe. The reason is that other languages don't enforce Rust rules and guarantees, and Rust can check them, so responsibility falls on the programmer to ensure safety. Okay, what can we see from here? Extern C. Within the unsafe extern C block, we list the names and signature of external functions from another language we want to call. The C part defines which application binary interface the external function uses. Application binary interface defines how to call the function at the assembly level. The C ABI is the most common and follows a C programming language application binary interface. Information about all the ABIs Rust supports is available in Rust reference. Just curious, do they have Rust system? Nice, Win64 ARM. Interesting. Win64 is here. It'd be interesting to see something like, oh, we have Win32 API. Oh, nice. Okay, let's come back. Every item declared within an unsafe extern block is implicitly unsafe. However, some FFI, it was FFI again. Foreign function interface, FFI. Where were we? Okay, however, some foreign function interface functions are safe to call. For example, the abs function from C's library does not have any memory safety considerations, and we know it can be called with any I32. In cases like this, we can use the safe keyword to say that this specific function is safe to call even though it is an unsafe extern block. Once you make the change, calling it no longer requires an unsafe block as shown in 20-9. Marking a function as safe does not inherently make it safe. Instead, it's like a promise you are making to Rust that it is safe. It is still your responsibility to make sure that promise is kept. Okay. Calling Rust functions from other languages. Can use extern to create an interface that allows other languages to call Rust functions. Instead of creating the whole extern block, we add the extern keyword and specify the application, what is ABI again? Application binary interface. To use just before FN keyword for the relevant function, you also need to add a sharp unsafe no mangle annotation to tell the Rust compiler not to mangle the name of this function. That is mangling. Mangling is when a compiler changes the name we've given a function to a different name that contains more information for other parts of the compilation process to consume, but is less human readable. Is it a form of obfuscating also? Maybe. Maybe we can search. Obfuscating. So, obfuscating code with name mangling. Name mangling changes the name of your classes. Okay, so somehow they are related. Every programming language compiler mangles names slightly differently. So for a Rust function to be nameable by other languages, you must disable the Rust compiler's name mangling. This is unsafe because there might be, so there's a possibility of name collisions across libraries without the built-in mangling. So it's our responsibility to make sure the name we choose is safe to export without mangling. Okay, in the following example, we make the call from C function accessible from C code. After it's compiled to a shared library and linked from C. Unsafe, no mangle. Okay. This usage of extern requires unsafe only in the attribute. Unsafe only in the attribute. Not in the extern block. Okay. Accessing or modifying a mutable static variable. In this book, we've yet talk about global variables, which Rust does support but can be programmatic with Rust ownership rules. If two threads are accessing the same mutable global variable, it can cause a data race. In Rust, global variables are called static variables. Listing 20-10 shows an example declaration and use of static variable with a string size as value. Okay, so how to create static variables. Static hello world, all caps, string slice reference, hello world. Static variables are similar to constants, which we discussed in constants in chapter 3. The names of static variables are in screaming snake case by convention. Static variables can only store references with the static lifetime, which means the Rust compiler can figure out the lifetime and we aren't required to annotate it explicitly. Accessing an immutable static variable is safe. A subtle difference between constants and immutable static variables is that values in a static variable have a fixed address in memory. Okay, because it's static. Static variable. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate their data whenever they're used. Another difference is that static variable can be mutable. Static variables can be mutable. Accessing and modifying mutable static variable is unsafe. Unsafe. Okay, so 20-11 shows how to declare, access, and modify a mutable static variable named counter. Okay, mutable static variable named counter. Add to count. Unsafe. Okay. It's being incremented. this part is unsafe. Then in main, you have unsafe. Okay, so unsafe block calling add to count. So unsafe when calling it, unsafe when counter is being incremented, and then unsafe for this entire thing. As with regular variables, we specify mutability using mut keyword. Any code that reads or writes from counter must be within an unsafe block. This code compiles and prints counter 3, counter equals to 3, as we would expect because it's single-threaded. Having multiple threads access counter would likely result in data races, so it's undefined behavior. Therefore, we need to mark the entire function as unsafe and document the safety limitations, so anyone calling the function knows what they are and are not allowed to do safely. Whenever we write unsafe function, it's idiomatic to write a comment starting with safety and explaining what the caller needs to do to call the function safely. Likewise, whenever we perform an unsafe operation, it would be idiomatic to write a comment starting with safety. It is idiomatic to write a comment starting with safety to explain how the safety rules are upheld. Additionally, the compiler will not allow you to create references to a mutable static variable. You can only access it via raw, okay, so it's only by a raw pointer created with one of the raw borrow operators. That includes in cases where the reference is created invisibly, as when it is used in the print line macro. The requirement that references to static mutable variables can only be created via raw pointers helps make the safety requirements to use them more obvious. With mutable data that is globally accessible, it's difficult to ensure that there are no data races, which is why Rust considers mutable static variables to be unsafe. Where possible, it's preferable to use the concurrency techniques and thread-safe smart pointers as we discussed in chapter 16. So the compiler checks that data access from different threads is done safely. Implementing an unsafe trait. We can use unsafe to implement an unsafe trait. A trait is unsafe when at least one of its methods have some invariant that the compiler can't verify. We declare that a trait is unsafe by adding the unsafe keyword before trait. So unsafe trait. And making the implementation of the trait as unsafe, as shown in here. By using unsafe IMPL, we're promising that we'll uphold the invariants that the compiler can't verify. As an example, recall the sync and send marker traits we discussed in extensible concurrency with sync and send traits. In chapter 16, the compiler implements these traits automatically. If our types are composed entirely of other types that implement send and sync. If we implement a type that contains a type that does not implement send or sync, such as raw pointers, and we want to mark that type as send or sync, we must use unsafe. Rust can verify that our type upholds the guarantees that it can be safely sent across threads or accessed from multiple threads. Therefore, we need to do those checks manually and indicate as such safe. Accessing fields of a union. Okay. What is a union? Okay. Final action that works only with unsafe is accessing fields of a union. A union is similar to struct, but only one declared field is used in a particular instance at one time. Unions are primarily used to interface with unions in C code. Accessing union fields is safe because Rust can't guarantee the type of data currently being stored in the union address in the union instance. You can learn more about unions in the Rust reference. Let's take a look. So unions has a topic of its own. Oh, okay, so it's here. Which book is this? References. Like a cheat sheet. Okay, that's good. Maybe we can cover that in future videos. Okay, using Miri to check unsafe code. And Miri. Okay, when writing unsafe code, you might want to check that what you have written actually is safe and correct. One of the best ways to use Miri, an official Rust tool for detecting undefined behavior. Whereas the borrow checker is a static tool that works at compile time, Miri is a dynamic tool that works at runtime. It checks your code by running your program or its test suite and detects it when you violate the rules it understands about how Rust should work. Using Miri requires a nightly build of Rust. We should talk more about how Rust is made and nightly Rust. You can install both nightly version of Rust and the Miri tool by typing Rust up plus nightly component. This does not change what version of Rust your project uses. It only adds the tool to your system so you can use it when you want to. You can run Miri on a project by typing cargo or cargo nightly Miri test. For example of how helpful this can be, consider what happens when we run it against listing 20-11. Miri correctly warns us that we have shared references to a mutable data. Where does it show? Okay. Here Miri issues only a warning because this is not guaranteed to be defined behavior in this case. To be undefined behavior in this case. And it does not tell us how to fix the problem, but at least we know there's a risk of undefined behavior and can think about how to make the code safe. In some cases, Miri can also detect outright errors, code patterns that are sure to be wrong, and make recommendations about how to fix those errors. What else is here? Miri also does not cover every possible way your code can be unsound. Put another way, if Miri does catch a problem, you know there's a bug. But just because Miri doesn't catch a bug doesn't mean there is a problem. It can catch a lot though. Try running it on the other examples of unsafe code in this chapter and see what it says. Okay, you can learn more about Miri in this GitHub repository. Let's see, Rustlang Miri. Undefined behavior detection tool for Rust. It's quite long. Okay, so when to use unsafe code? Using unsafe to use one of the 5 superpowers just discussed isn't wrong or even frowned upon, but it's trickier to get unsafe code uh, correct because the compiler can help uphold memory safety. When you have a reason to use unsafe code, you can do so. And having explicit unsafe annotation makes it easier to track down the source of problems when they occur. Whenever you write unsafe code, you can use Miri to help you be more confident that the code you've written upholds Rust rules. For a much deeper exploration of how to work effectively with unsafe Rust, read Rust official guide to the subject. Rust to Nomicon. I think we might have accessed this before. Yeah, everything unsafe here. This could be the dark arts of unsafe Rust. Okay. Advanced traits. Okay, we first covered traits in Traits Defining Shared Behavior, Chapter 10, but we didn't discuss the more advanced details. Now that you know more about Rust, you can get into the nitty-gritty. Okay, associated types. Associated types connect a type placeholder with a trait such that the trait method definitions can use these placeholder types in their signatures. The implementer of a trait will specify the concrete type to be used instead of the placeholder type for a particular implementation. That way we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. We've described most of the advanced features in this chapter as being rarely needed. Associated types are somewhere in the middle. They're used more rarely than features explained in the rest of the book, but more commonly than many of the other features discussed in this chapter. Okay, let's see. One example of a trait with an associated type is the iterator trait that the standard library provides. The associated type is named item and stands in for the type of the values, the type implementing the iterator. The definition of the iterator trait is as shown, okay, here. The type item is a placeholder, and next method's definition shows that it will return values of type option. Implementers of the iterator trait will specify the concrete type for item, and the next method will return an option. Next method returns an option containing a value of that concrete type. Associated types might seem like a similar concept to generics. In the latter shows us to define a function without specifying what types it can handle. To examine the difference between two concepts, we'll look at an implementation of the iterator trait on a type name counter that specifies item is I32. Okay. Implement iterator for counter. The syntax seems comparable to that of generics, so why not just define the iterator trait with generics? Okay, here using generic, T would be the type, The difference is that when using generics, as in 20-14, we must annotate the types in each implementation. Because we can also implement iterator string for counter or any other type, we could have multiple implementations of iterator for counter. In other words, when a trait has a generic parameter, it can be implemented for a type multiple times, changing the concrete types of the generic type parameter each time. When we use the next method on counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. With associated types, we don't need to annotate types because we can implement a trait on a type multiple times. 20-13 with a definition that uses associated types, you can choose that the type of item will only be used once. Because there can be only one IMP iterator per counter. We don't have to specify that we want an iterator U32 values everywhere that we call next on counter. Associated types also become part of the traits contract. Implementers of the trait must provide a type to stand in for the associated type placeholder. Associated types often have a name that describes how the type will be used. And documenting the associated types in API documentation is good practice. Default generic type parameters and operator overloading. Okay. When we use generic type parameters, we can specify a default concrete type for the generic type. This eliminates the need for implementers of the trait to specify a concrete type if the default type works. You specify a default type when declaring a generic type with placeholder type as concrete type syntax. A great example of a situation where this technique is useful is with operator overloading, in which you customize the behavior of an operator, such as in particular situations. Rust doesn't allow you to create your own operators or overload arbitrary operators. You can overload the operations and corresponding traits listed. Okay, so standard ops by implementing the traits associated with the operator. For example, in this thing 20-15, we overload the plus operator to add 2 point instances together. We do this by implementing the add trait on a point struct. The add method adds the x values of 2 point. Add method. Instances and the y values of 2 point instances to create a new point. Where's this? The add trait. The default generic type in this code is within the add trait. Here's the definition. Add. Okay, we have add. Okay, add is not shown in there. Again, just add here. Okay, so this is new. This code should look generally familiar. A trait with one method, okay, trait with one method and associated type, RHS self. This syntax is called default type parameters. The RHS, generic type parameter, or shorthand for right hand side, RHS, right hand side, defines the type of RHS parameter in the add method. If we don't specify a concrete type for right hand side when you implement the add trait, the type of RHS will default to self, which will be the type we're implementing add on. When we implemented add for point, we used the default for RHS because we wanted to add 2 point instances. Let's look at an example of implementing add and trait where we want to customize the RHS right hand side type rather than using the default. We have two structs, millimeters and meters, holding values in different units. This thin wrapping of an existing type in another struct is known as the new type pattern, which we describe in a more detail in this one. Using new type pattern to implement external traits on external types. We want to add values in millimeters to values in meters and have the implementation of add do the conversion correctly. We can implement add for millimeters with meters as the RHS as shown in 20-16. Okay, millimeters, meters, add meters for millimeters. Implementing the add trait on millimeters to add millimeters to master. No, not master. To add millimeters to meters. To add millimeters and meters, okay, millimeters and meters, we specify IMPL add meters to set the values of the right hand side type parameter instead of using the default of self. What is that? Add meters. Okay, you'll use default type parameters in two main ways: to extend a type without breaking existing code, to allow customization in specific cases most users want. Standard libraries add trait is an example of the second purpose. Usually, you'll add two like types, but the add trait provides ability to customize beyond that. Using default type parameter in the add trait definition means you don't have to specify an extra parameter most of the time. In other words, a bit of implementation boilerplate is needed, making it easier to use the trait. The standard leverage add trait is an example of second purpose. Usually you'd add two types, but the add trait provides the ability to customize beyond that. Using a default type parameter in the add trait definition means you don't have to specify extra parameter most of the time. In other words, a bit of implementation by the trait isn't needed, making it easier to use the trait. The first purpose is similar to the second, but in reverse. You want to add a type parameter to an existing trait, you can give it a default to allow extension of the functionality of the trait without breaking the existing implementation code. Oh, so today, most of the things here are a lot of things to read. Okay, but don't worry. We'll go through it once again until we can understand it. All right, so let's end here for now, and then we try to do a review tomorrow once again and go through the advanced features of Rust. Thank you so much for joining me today. Before I finally end, let me thank my supporters.